Well, thank you all for coming. Um, I think I've met all of you uh, at various points in when I was at UCSB. But I'm Steven, and this diffuse scattering and 3D Delta PDF workshop is going to combine, I guess on the next slide should show it. It's going to combine a little bit of, foundational like theory, and we'll discuss like what is diffuse scattering, what causes it, and how we can use basically Fourier methods to get out some real space information. And then the second portion of this workshop is meant to be sort of interactive. So the idea would be to have each of you sort of following along in a Jupyter notebook. All the code is already there. You won't have to really write anything. You'll just be able to like sort of play around with numbers and see how various parameters like change or affect the quality of what you're doing. And in that process, we'll sort of discuss like what are the common strategies for making the 3D Delta PDF work, and what are some common pitfalls of where it can go wrong, where you might not notice that what you're looking at is actually just an artifact and not actually what you want to refine out of the data. And then lastly, I'll discuss how computational modeling of disordered systems goes hand in hand with the 3D Delta PDF method, and how they're sort of getting good 3D Delta PDF results almost always demands that you do some sort of computational modeling because the interpretation is quite challenging. And we won't actually walk through like an interactive simulation, but you'll have all the files necessary to do so on your own, and we'll sort of just run it on my computer because the installation of the software is kind of a pain in the neck. So I figured for today it would be easier just to have everybody working in Python because I feel like it's a little bit easier to install. Before we begin, though, does everybody have Jupyter Notebook, and does everybody know how to use a Jupyter Notebook? And if you don't, can you speak now? All right, I'm gonna take that as a yes. And feel free to stop me with any questions. This is meant to be pretty casual, so the more discussion we have, the better. I'm going to flash up a bunch of sort of guiding slides, but there's definitely more details to all of this. So if you think of a question or if you think of a use case for this kind of stuff and you have questions about how that would work, feel free to chime in. So to start off our discussion about disorder and diffuse scattering, um, we want to think about how disorder manifests in real materials. So when we're thinking about an ideal material, we think about the unit cell and this lattice. Oh, there's Raina. We think about a unit cell and the lattice, where the ideal lattice is sort of just every atom is perfectly sitting on its site without any displacement away. But there's always some sort of thermal disorder, which is one type of disorder at finite temperature, which causes what we'll call displacements or displacive disorder. So in comparison to the picture on the left, this picture in the middle, every atom is sort of moved randomly away from its origin, as denoted by those dotted lines. That's one type of disorder that's sort of always present in real materials. And then another type of disorder that's pretty hard to avoid is what we'll call occupational or substitutional disorder. So this is things like vacancies or impurity atoms, or maybe you're making an alloy of two different elements. Um, these forms of disorder are more or less, ubiquitous in all the materials we study. And even though we like to think of them as sort of this ideal crystal structure, uh, there's always some sort of defects, right? And more often than not, these defects are not randomly placed. Sometimes they can be, and a lot of times they can be correlated with each other. So disorder on one site can interact with disorder on another site and create correlations. So that's what this slide is getting at. So disorder isn't always random, even though the word sort of sounds random in itself. So when we think about the disorder in these compounds, we don't have to just talk about atomic sites, like elements occupying a different site. We can think about magnetic degrees of freedom, like spins, charges, and we can think of lattice degrees of freedom, like displacements. And just to give an example of like a checkerboard pattern of sort of a two-atom alloy of black and gray atoms, if I had random disorder where there's no interactions between occupations of different sites, I would just get a random map, which kind of looks like TV static, right? There's no probability distribution of like, or there's sort of a 50-50 probability distribution of finding a black atom next to a white or a gray atom. In the case that you have some sort of energy scale or some sort of interaction that says, hey, black atoms want to be with other black atoms and gray atoms want to be with other gray atoms, and that's energetically favored, then as your material grows, you might find that there are clusters of black atoms and clusters of gray atoms. So this is a form of what we call short range order, in contrast to long range order, where these pockets are sort of infinitely large. Short range order only persists across a few unit cells before sort of degrading. And on average, if you look at these two pictures, they're the same composition, right? It's the same 50-50 mixture of gray and black atoms, but there's some underlying difference that's happening at short length scales that would be, probably strongly affect the properties. The other opposite case is, let's say, black atoms are repelled from other black atoms and gray atoms are repelled from other gray atoms. In that case, what would be favored is sort of like a checkerboard pattern. And so a short range version of that is what's shown here. And I guess it's kind of hard to see, but if you like stand up and like step away from your computer and like squint your eyes, you can see domains that are similar to the picture in the middle. You can see the defects that sort of form between the domains of checkerboard. Maybe if you blur your eyes or squint a little bit, you could maybe see a uh, big domain wall here. So these are just examples of like a substitutional degree of freedom. But we'll get into other degrees of freedom in a second. So what happens when we have short range order like this is that when we perform a scattering experiment, say like a diffraction experiment, the correlations of these defect modes can actually give rise to some features in the scattering, which are known as diffuse scattering. So to illustrate this, I took a Fourier transform of the pictures I showed you on the previous slide. So that's what's shown in the upper left here. This is the sort of atomic model where there's totally just random disorder. There's no correlations between each neighboring site. And when you take the Fourier transform of that, you get this diffraction pattern, which just looks like your regular set of Bragg peaks. Okay, so for those of you who have taken materials 209A, this might, sound a little bit familiar, the discussion we're going to get into. Now, when we take a Fourier transform of the short range ordered model that we had on the last slide, you see that there's this additional intensity, this sort of like blurry sort of feature in the background. And that's what we're calling this diffuse scattering. It has a long sort of like, tail around each Bragg peak that extends outward. And in fact, it looks like it's sort of connected horizontally and vertically. That's what we might see in the case of positive correlations. And when I say positive correlations, I mean that like in sort of like a ferromagnetic sense, where like atoms want to be with other like atoms. And the opposite case we talked about was negative correlations, right? Where you want this alternating pattern. And you see that now the diffuse scattering has moved away from the Bragg peaks and now it's located at the half integer positions in reciprocal space, which is what you might expect, right? If you have a doubling of your unit cell, which is what happens when you have an alternating pattern. Okay. So diffuse scattering can get a lot more complex than this. It can in fact have a lot of structure and a lot of texture, but this is sort of the simplest case I could come up with that sort of illustrates these three examples. So one thing we can do then is we can just take out the Bragg peaks and just look at the diffuse scattering component. And we'll get into why we can do that in a second. But this is what is underlying those Bragg peaks in each case. So here there's just some sort of like, background diffuse scattering. Here there's integer diffuse scattering, and here there's half integer diffuse scattering. So a little bit of math. Sorry. Scattering in general is a Fourier-based technique. So when we think about the mathematics of scattering physics, we have to invoke Fourier transforms. And so I'll sort of walk you through why that's useful for this DeltaPDF stuff we're going to talk about. So one thing you might remember from sort of introductory diffraction is that the structure factor, right, which is f of q, is the Fourier transform of the electron density in the unit cell. So we take all the atoms in the unit cell, we add up all their contributions, and we take a Fourier transform, and we get the structure factor which belongs to that unit cell. So it kind of makes you wonder, why can't I just apply an inverse Fourier transform to my diffraction pattern and just get back the image of the electron density, like straight out of my diffraction data? And then further than that, if we have diffuse scattering, what if I just apply an inverse Fourier transform to just the diffuse scattering? Can I get information or a picture even of the disorder that's underlying, that diffuse scattering? So there's one complication, which you might be familiar with, is that we don't measure the Fourier transform directly in a diffraction experiment. We measure the intensity, which is I of q, and that is the amplitude squared of the diffracted waves, which here I'm representing as capital psi of q. So that amplitude is coming from waves that are interfering from different pairs of unit cells that are located at different locations within the crystal. So that's what this phase term is saying here, which I'm going to have you ignore. But the important part is that this is basically a sum of the Fourier transforms pairwise across the crystal. So there's two terms here. Okay. And if we plug in our definition for the structure factor that we had on the last page, and we do a lot of simplification, we find out that the intensity is nothing more than the Fourier transform of a pair of electron density. Okay. So we'll go into what that means on the next slide, but already we can see that we're starting to get closer to where we can just apply an inverse Fourier transform to what we measured during the experiment. So what information do we get from inverting the intensity that we get out from a diffraction experiment? If we apply the inverse Fourier transform, we get rid of this orange stuff, and we're left with this convolution integral in the middle. And so to get into what that is, that itself is what we call the pair distribution function, or PDF. Okay. And the interesting thing about this function is that it's convoluting, or not convoluting, the wrong way to say it, convolving the convolutions here, convolving the electron density with itself at different positions. And so what that allows you to do is say that wherever there's a peak in this convolution, that must be where there's pairs of electron density that are sort of separated by some distance, which might, we'll define here as R1 minus R2 or R2 minus R1. So a picture of that would be sort of two atoms that are separated by some distance, and then that distance will be reflected in this function. And we have more visual examples in the following slides, so don't feel like you need to fully understand this. But what we're going to call this is sort of correlations between the electron density. So some visual examples in just one dimension to sort of orient us in a visual sense. If I have, the simplest unit cell that I could possibly have in one dimension, which is just a single atom, and I have that tiled, the electron density would look something like this. It would be like sort of like a delta function that's centered at each integer position in real space. Okay, so the x-axis here is just, real space position, and the y-axis is the electron density. Now, if I take a Fourier transform of that and square the amplitude, I'll get my my diffraction pattern. So that's what's here. This is a calculated version of the Fourier transform squared of this, okay? And this is what you might measure, right? This is what you might get out of a diffraction experiment. And then if you wanted to go take the inverse Fourier transform of that to get back that pair distribution function, you would get something that looks like this, which is, remarkably similar to the real space picture that we started with of the actual crystal. It's just a little bit different, a little bit broader. Things will change if we have a different crystal. So let's say I have a crystal where I have alternating atoms, one big and one small. The electron density might look something like this, where this atom has more electrons and this atom has a lot less. The Fourier transform of that would look slightly different. Okay. Here I'm keeping the lattice units the same. So this, might look like half integer peaks, but that's only because I'm keeping the unit cell distance as one unit here, just for comparison between the two examples. But you see our diffraction pattern changed, and as a result, our PDF should change as well. And so what we get out is in the PDF, we see this alternating pattern, which is representative of this alternating pattern of atoms in real space. So already we see we can get useful useful information from the PDF that represents what our atoms are looking like in real space. Now, the last example, which I think is the most insightful, is when those atoms are not equally spaced, okay? So imagine these are sort of pairs of atoms or molecules, and the electron density might look something like this. The Fourier transform would look something like this. I guess the Fourier transform squared, I should say. And then the PDF would look something like this, okay? So you see how this is not exactly the same as the electron density we started with, right? So it's not just as simple as getting a picture of the electron density that we started with. The pair distribution function has a little bit more complexity to it. So to read into this, we're looking at, as we said earlier, correlations between atoms at a certain distance. So the information that we're getting out here is a picture of all the interatomic distances that exist within our sample, all superimposed on the same plot. So on the right side, I have an atom, I don't know what that is, a third of a unit to the right, which corresponds to this distance between this atom here and this atom here. I also have an atom that's an integer distance away, right? Or two integer distances away, which is this long red arrow here. And then on the left side, there's an interatomic distance that I observe from this atom to this atom. And then, 2 units away, there's also the distance between this atom and 2 units away, this blue atom. Okay, I'll pause there because I'm not sure how well I explained that. So I'll let y'all speak up if you have any questions. All right, I got thumbs up. All right. So now the question becomes, what happens when we isolate just the diffuse scattering and try to do the PDF with that, okay? So we're going to return to this example that we have of an alloy of two different atoms. So let's call them A and B, which are the black and the gray atoms. If we plug in a theoretical description for a two-atom alloy, this is what the Fourier transform ends up looking like. And I don't need you to read all these terms, but what I do want you to see is that the scattered intensity becomes a sum of two different terms, and they're independent of each other, okay? So one of those terms, the term on the left, is just the Bragg peaks, okay? And those Bragg peaks, if you look at the scattering factor here in front, this is usually like what we call lowercase f and like our structure factor. This is an average of the two electron densities of atom A and atom B. So what I want to say about this is then this is the average structure. Okay, so it's like an average picture where you have some sort of like hybrid of atom A and B on every site. Okay. The average structure is what creates the Bragg peak. So that's the crystalline component. Now the diffuse scattering is coming from this term, and this term has this term, this coefficient CJK, which is a correlation coefficient between two sites J and K. And this is related to the probability of finding the probability of finding different pairs of atoms on different sites. And when the disorder is totally random, in the totally random case, this coefficient is going to be zero. There's no correlations whatsoever. So if it is totally random, we're just going to get Bragg peaks, right? This term is going to go to zero. If there are correlations, if there's not like an uneven probability distribution of finding, say, black atoms next to black atoms, if it's not totally random, this coefficient won't be zero, and then this term will start to contribute a little bit of diffuse scattering to our overall intensity. So again, this term provides the diffraction from the average electron density, and then this term only appears when there's correlations between any two sites, as there would be, say, in this picture. And then the Fourier transform of these individual components would give us the average structure, and this component would give us deviations from the average structure, okay? And so to more concisely write this, we can think about this as just the Bragg intensity and just the diffuse intensity in our data. And we can remove the Bragg peaks from our data and just isolate what we'll call the local deviations from the average structure. And so we really can use a Fourier transform to get out just pictures of the changes in the local structure and really get a real space picture of our disorder. All right, so let's see what that looks like, because that was a lot of math. So if I take the random case and I take this diffuse scattering and I invert it, I apply an inverse Fourier transform, I get this pattern here, which is nothing, right? So this is the regular PDF on the left, and this is the changes in the PDF, what we'll call the DeltaPDF on the right side. So the average structure looks something like this. There's an atom on every site. Whoop-de-doo. Big surprise. But the DeltaPDF doesn't show anything because there's no correlations, right? So the average structure is the same as the local structure. Even though there's two atoms, black and gray, there's no enhanced probability of finding one or the other on every site. Now, in the case that we have positive correlations and we have these sort of like domains, if we take the Fourier transform, that's hard to see. If we take the Fourier transform of just the diffuse scattering, you see how there's a little bit of red intensity at each of these sites? That means that there's an enhanced probability that you're going to find an atom of the same type nearby, which is what we see in the real space picture, right? If I just point at any black atom, there's a really high probability that all of its neighbors are also black atoms, right? And then this one is a little bit more interesting when we have negative correlations. If I take the diffuse component and invert that, I get an alternating pattern of red and blue. So positive and negative changes in the electron density. And that's because I can either have, how do I want to say this? The increase and the decrease in the local electron density are meaning that you can have an atom that has the same electron density or lower electron density, or alternatively, the same electron density or higher electron density than the average. Okay, questions about that?
So
Oh, yeah.
it's picking up the electron density variation, right?
Yes.
Can you also pick up any spin-spin correlation
If you did
from
this
delta
on
PDF?
if you did this on a neutron experiment, for sure, yeah. Like, you know,
Okay.
if you for example take the spin ice diffuse scattering, which is like a really well-defined like bow tie shape scattering pattern, and you apply a Fourier transform to just that spin ice texture and get rid of
Mm-hmm.
all the Bragg
Mm-hmm.
reflections, you will get out a picture of the correlations that exist in the spin ice structure.
Okay,
Yeah, in the DeltaPDF.
I see.
Mhm.
Thank you.
This whole discussion today will just be about X-rays because I think that's a little bit more familiar, but definitely this can be applied to neutrons and for spins and things like this.
Okay.
Okay. So what we've looked at so far are substitutional correlations, right? We've seen that we can have correlated occupation of sites. There's other degrees of freedom that we might be interested in, say displacements, where if one atom moves to the right, all of its neighbors will also tend to move to the right. There's also what we call size effect correlations, which are sort of a combination of the two. So that could be because, you have occupation of a site by a tiny little atom, and because that atom is smaller, all the atoms around it will tend to sort of collapse inward. And so you get a combination of substitution correlated with displacement. Okay. And for all three of these examples, we want to see what kind of features we might expect in the delta PDF. And the reason we want to do that is because, usually when you grow a crystal, you don't really know what's happening with the atoms at the local scale. The first thing you do is, take a diffraction pattern. So you don't always have a good understanding of what's going on atomistically, but you want to be able to know how to interpret the delta PDF once you obtain it from your diffraction. So looking first at the substitutional correlations, which is sort of what we already did in the last few slides, the local structure, let's say in this alternating case, if I have opposite atoms on nearby sites, the local structure 1 unit cell away would be slightly lower than the average structure. So let's say, this one has a structure factor or a scattering factor of 1. This one has a scattering factor of 2 because maybe it has, twice as many electrons. The average will be the average of 1 and 2, which is 1.5, right? So if this atom over here is, less than the average, then you will get a local structure that is slightly less than the average value. That was a lot of words to say a very simple thing. My bad. So if you subtract these two, you get the difference between the local and the average, which looks like this negative peak. Okay, so that'll tell you about the change in the local structure. And what that looks like in 2 dimensions, oh, hold on. What that looks like in 2 dimensions is not on the slide because I'm dumb. All right, there's the 2 dimensional version. So what that might look like is a negative Gaussian peak in your delta PDF. Okay. So whenever you see like a Gaussian looking blob, that's usually indicative of something like a substitutional correlation. Now it can get more advanced than this. So let's look at displacive correlations. Let's assume that these atoms, nearby atoms are attached by a rigid spring. Okay. So in the sense that if one atom moves to the right, it's going to push the other atom a little bit to the right as well. So their displacements are related to each other, right? They're correlated. So on average, every atom is sort of vibrating, right? Let's say that's due to thermal fluctuations. So its electron density is sort of spread out along some coordinate, right? But locally, the electron density is really more sharply peaked at the unit cell length, at the lattice parameter, because when one atom moves to the right, it tends to be rigidly connected to its neighbor, right? And so the difference between these two will look something like this. It'll look like this sort of triplet shape where you have a negative lobe and then a positive lobe and then a negative lobe, which we get by subtracting these two. And in 2 dimensions, that looks something like this. Okay, so it looks like this like sort of dumbbell shape. And then the last one,
Uh,
yeah, go ahead.
can I ask something?
Yeah.
So usually when we do extra diffraction, we take care for the instrumental broadening. So
Mhm.
here it's already taken care of.
Define taken care of, I guess. Because these peaks right here I'm talking about are in real space.
Mhm.
So these peaks are due to like these are the electron densities as a function of like distance, right?
Yeah.
So, I mean, ideally the instrumental broadening in your diffraction experiment should be much, much narrower than the peak width of the diffuse scattering, right?
Okay.
Because diffuse scattering inherently is like super broad.
Mm-hmm. Okay.
Yeah. Okay. So the last example we had was these size effect correlations. And these are, a combination of occupation and local displacement. So what happens here is that if I have a site that gets replaced by this smaller atom B, then the neighboring atom, which we'll call A prime, will tend to collapse inward toward that site, right? And in addition to that, if you look from A prime's perspective, not only is it collapsing towards B, but it's also moving away from its neighbor, which should have been at the its ideal lattice position. So the distance between A prime and their neighbor has also increased. And so what we'll get then is locally, you'll see sort of this two-peak feature where there's a combination of some electron density at a shorter distance than you might expect, and there's some electron density at a longer distance that you might expect. Okay. And the average structure still looks like this nice, average position. And so when you subtract these two, you get a dumbbell shape. Okay. And or not a dumbbell shape, a dipole shape. And in 2 dimensions, what that looks like is this dipole right here. Okay, cool. So this example is what we're going to work with in the interactive section that we'll go into next. All right. So just to give you an overview of how the 3D Delta PDF workflow is going to work. So typically when we get experimental data, it comes looking like this, right? There's like a finite detector size and there's a lot of artifacts and things like that. So one thing that we do first is to maximize the range of reciprocal space that we can access. We take a slice of the data and we basically reconstruct the rest of reciprocal space using the symmetry operations that are inherent to that space group or point group. And that allows us to get a cleaner data set that has more information that we can use for the Fourier transform. Okay. The next step would be to punch out all the Bragg peaks. And so we basically identify where all the Bragg peaks are, and then we punch them out. We just delete them from the data set. Okay. And then you can't just like apply a Fourier transform to that data set. You actually have to fill in the gaps that you created when punching out the Bragg peaks by basically applying a blur to the entire image that sort of smears out the data and fills in the holes using values around it. And so we call that the interpolation step. And then the next step would be to pad the data with zeros, which I'll explain in a second. The short answer to why we do that is because it increases the resolution after the Fourier transform. And because we're basically padding the data with a bunch of zero values, the data set gets really huge. So the example we're going to do today, we're going to be able to do on our computers. But in general, if you're working with an actual 3-dimensional data set from like an actual like scattering experiment, you will probably need to do this on a cluster, on one of the fat nodes, which that's what they're called. Uh, the fat nodes have 1.5 terabytes, I think, of no 1.5, yeah, 1.5 terabytes of memory. And so you can be able to work with like really large data sets and get a good Fourier transform out. If you tried to do this on your regular computer, your computer would run out of memory very fast. Okay, yeah, last step, just apply the Fourier transform to that data set and you get a nice Delta PDF, which can be quite complex. Okay. So the first example we're going to talk about is an example of disordered vacancies. And so just to prime you for what we're going to do, the real space picture is that there are vacancies in this square lattice compound or this simple cubic compound, and around every vacancy, the atoms are displaced towards the vacancy, just like we saw in that size effect example. Okay. So with that, I have slides, but I'm also gonna bust out a Jupyter notebook. So if you all could, let me share my screen.
I have a quick question.
Yeah, what's your question?
So, wouldn't it be better to look at the data at very low temperatures because then you minimize the thermal disorder diffuse scattering source? Like,
It depends on the scattering because I had one compound where the diffuse scattering was strongest at 300K, and that's what I was
oh,
interested in. Yeah, but in
okay.
general, yes, lowering the temperature would minimize the thermal contribution to the diffuse, which in a lot of cases would help you isolate the diffuse scattering. Yes.
Yeah, yeah.
Mhm.
Thank you.
Yep. Okay, so you all should have downloaded the folder that looks like this, right? Do we have that up? Okay. And the example we're going to go into is this vacancies folder. So I'm going to ask you to open that up. And then there's a bunch of files in here, but really all we need to do is open a command prompt window here. So I'm going to go into the address bar here, and I'm on Windows. If you have a Mac, I'm sorry, I don't know how to help, but you can open terminal and just change your directory until you get here. If you're on Windows, you can just go into the address bar and type in CMD, and then you get out this very conveniently located command prompt window, which I can't seem to move. Come on now. Okay, so this is my command prompt window, right? And if you follow the instructions, you should have a conda environment called NXS, neutron and X-ray scattering. Okay. If you don't have that, or if you are just starting to do that now, there's instructions in the Word doc I sent out. So I'm going to activate that environment, and inside that environment, oh, rip, I actually have it called something different on my computer. Yeah, okay. Within this environment, I should have this package called Nexus Analysis Tools, and that's going to allow us to use the tools relevant for the DeltaPDF. So I just typed pip show, and that confirmed that I had that installed. So if you want to confirm that you have it installed, just type in pip show NXS Analysis Tools. Okay, and since there's so few of us, I'm happy to address any troubleshooting. Hopefully it won't take too much time. Andrea.
Hi, so sorry. Andrea joined the meeting now too, but we're trying to dual screen.
Okay. Um,
Oh shoot.
so is this working for everybody? Do you have this up and running? Okay, give me a thumbs up. Okay, seems like
I just
most
had
everybody.
my command prompt won't open from the
Yeah.
sorry, could you I was trying to get my command prompt to change directory,
You can
Uh-huh.
also
but you can also just open in that folder.
If you are on Windows, you should be able to go into the address bar and just type in CMD.
Okay.
It should just open it there. If not, you just have to use CD and then drive your way through your folders to get to the folder that we're working in. I'll pause the recording for now. Oh wait, no, that was my screen sharing. All right, I'm resuming the recording. So we've opened Jupyter Lab. We're going to go ahead and open this vacancies.ipy notebook. Okay, and so wonder how I could do this. Let me see if I could. Might be a little convoluted, but. Mhm. Yeah, this might work. Okay, so step one, we're going to import all the functions that we need. So we're going to need plotting functions from matplotlib. We're also going to need the general tools from the Nexus Analysis Tools package. But this is saying from Nexus Analysis Tools, import all the functions and modules. And then from the pair distribution module specifically, import the DeltaPDF class. Okay, so if you haven't used Jupyter Notebook before, I'm going to use Shift Enter, and that runs the cell and then moves on to the next cell. Gonna take a second to load all that. Okay, it's done. You can tell it's done because that asterisk in this box turned to a number 1. All right, so let's visualize the scattering data that we've got. So the first thing we're going to do is load the data by running this load data function. Okay, so the vacancies scattering data is stored in a .nxs file or .nexus file. If you're not familiar with that file type, don't worry, because you won't have to work with it directly in this example. But it's cool because I mean, we'll see in a second. It allows you to very easily sort of drive around the scattering data and visualize things nicely. Okay, so if we load that, you see this output over here. It says I've loaded the data. The axes are HK and L, and then the signal is the photon counts. And then we see that we have 201 pixels along H and K and L. And then the scattering data is a 201 by 201 by 201 array. Okay, this is generally very small for a scattering data set. An actual single crystal data set would probably be like, thousands of pixels. So you can see how hard your computer works to carry out an operation on a 200 by 200 by 200 data set. All right. So the Nexus data format allows us to index the data using decimal values. So you can directly type in, I want to go to the HK0 plane, for example. This is in contrast to usual, Python, where if you type in 0, it gives you the first value in the array. But if you put in 0.0 as a decimal, it actually drives to the L equals 0 plane. Just kind of nice, right? Because that's what we're used to like talking about in terms of scattering data. Okay, so this plot slice function allows us to just take the data and index it however we want and plot a 2-dimensional slice. And then these 2 parameters here are going to control the color bar. Okay, so if I run this, I get out this data set here. I guess it's kind of impossible to show everything at once, but this is what we got out of that function. Okay, so we see that diffuse scattering is present, right? You see how these diffuse clouds are sort of located on what I'll call the nearer side of the Bragg peaks. That is actually because that is actually indicative of size effect correlation. So whenever you see diffuse scattering that's sort of asymmetric about the Bragg peak and it's located on one side, that's usually because of size effect. And we see already that this is this like highly structured diffuse scattering. So it's not as simple as just like some broadness around our Bragg peaks like we saw in the other example. Okay. So yeah, you could play around with the color map limits. You could also turn on log scale equals true or log scale equals false, and you'll be able to see this better or worse. Okay. So the next step then is to punch out the Bragg peaks. All right. So we're gonna basically design a mask that's gonna basically be true wherever our Bragg peaks are. So it's gonna have a value of 1, and the 1s are all gonna get punched out by our code. And then wherever this mask is 0, that's gonna be data that's preserved. Okay. So there's some considerations with this. You're deleting data, so don't overdo it. If you punch out too much, if you punch out too much data, you'll get lower data quality. And if you underdo it, if you leave any Bragg intensity at all, it will dominate the PDF because usually the Bragg intensity is orders of magnitude greater than the diffuse scattering. So you have to make sure to get all of it, but don't over punch. Okay. So the function we're going to use for that is this. Well, actually, sorry, I'm getting ahead of myself. I need to walk through to where we get that function. I'll just make this full screen for now. And I'm not going to run it like this. Okay. I could also probably zoom in, huh? Yeah, all right. All right, so this is plotting the H, K, L equals 0 plane. So you can see the axes here are H and K. This one here is the H0L plane. So you can see the x-axis is H and the y-axis is L. Okay. And so clearly is evidence for diffuse scattering in the background of the usual Bragg reflections. This is the perfect use case to apply the DeltaPDF technique. Okay, and so in order to do our Delta PDF magic, we need to create what's called this DeltaPDF object. And that DeltaPDF object is going to hold all the tools necessary for punching out the Bragg peaks and interpolating and then creating the Fourier transform. So I'm going to create an object by creating this thing called DPDF, and I'm going to assign that to the DeltaPDF class. So now this little guy right here, whenever I reference him, he's going to have all the tools necessary to help us out. Okay. So if I run that, I've initialized that guy. And step one is to set up the data and lattice information. So the first thing we need to do is we need to tell this guy where the data is. So we need to set the data, and we already have the data loaded, so we're just going to reference that variable. Okay. And then the next thing we need to do is set the lattice parameters. So we're just going to assume that it's a cubic unit cell with a lattice parameter of 5 angstroms. The most important thing here is the angles, because that really changes the symmetry of the data that we're going to transform. But changing the lattice parameter doesn't really make a difference because the image will just be like stretched or squeezed. There's not really like a big geometric difference. There's changes in the symmetry, but that won't actually affect any of the math that we're doing in this notebook. Okay, so I'm going to set that. Okay, step 2 is to generate a mask for all the Bragg peaks and any unwanted pixels. So usually that just takes the form of creating a sphere around each Bragg position because we know where the Bragg peaks are, right? We know that they're at, integer HKL values. And so we can use this function, generate Bragg mask, and just type in a punch radius in terms of lattice units, and that'll generate a mask, right? So let's say I wanted to punch out 0.2 reciprocal lattice units around each Bragg position. So I can go ahead and specify that and create a mask. Okay, and then I can plot the mask running this next code. And this is what the mask looks like. Okay. I could change that radius to be something bigger or smaller. Let's say I want it to be smaller. I'll do 0.05. And you see that it's getting reduced to like a couple pixels around each Bragg peak. Okay. For now, I'm going to keep it at 0.2.
Quick question.
Yep.
Sorry.
No, go ahead.
What if we don't have such a nice pattern? There is twinning and additional Bragg spots.
That will be the next cell that we're going to run. Okay. Yeah. Actually, do I have slides about that? Yeah, so maybe we'll go back to the slides for now. So we already saw that we can generate just a Bragg mask, which means that we're just punching out just the integer HKL values. And really, these are ellipsoids. You can stretch them along any of the principal axis of an ellipsoid. They don't have to be spheres. Now, the other method of punching out things is to generate what's called an intensity mask. So this is basically just going to threshold an intensity of your data set. So let's say any pixels that are above an intensity of 1 × 10⁹ are just going to get deleted. Okay. And to be a little bit more aggressive, you can change the radius of what you're punching out. And so basically what this is saying here is that it's punching out an additional 1 pixel around every offending pixel. Okay. And you can change that so that like, wherever I find a pixel of high intensity, let me just cover all my bases and punch around, that region a little extra. Okay. Questions, comments, concerns? So that's what you're seeing here in this mask. You can see they're not all perfectly the same size. It adapts to whatever intensity is present at each of the reflections. So the ones in the middle have higher intensity, so they get punched out a little bit more, and the ones around get punched out a little bit less. Okay. In this package that I wrote, there are tools for developing custom masks, so you could get really creative with it. You can like add and subtract different features to create like, I don't know, a happy face mask if you wanted to. Every data set is different. So you're going to need to get creative if you have a real data set. Like for example, like this is one of the data sets I worked with. real data often has a lot of artifacts. There's a background. There's like remaining intensity from the X-ray beam that you need to sort of get rid of. Um, and the goal with all of this, right, is to try to isolate the diffuse scattering with as much integrity as possible. And that's not always so simple when the detector looks something like this, right? So symmetrization helps a lot. Um, as we saw earlier, we can slice out what we find to be the cleanest part of reciprocal space and then basically reconstruct the rest. And that can help get rid of background. It can help make it easier to get rid of artifacts and things like this. But in general, this is the part you need to get right. Okay, so removing all the Bragg peaks, removing the artifacts, uh, is really gonna basically give the integrity of your data to your diffuse scattering only, right? You don't want any artifacts contributing something that's meaningless. Okay, so back to the Jupyter notebook. Um, yeah, I guess this is maybe helpful to point out. So even if you have this Bragg mask, if you're just looking at pixels around the integer Bragg positions, you can still say, I want a threshold, so you can basically like have a region of interest around each integer Bragg position and say within that sphere, only punch out the hot pixels. Okay. So that's what this thresh parameter is allowing you to do. That's what's shown here. Okay, we already saw that we can use this intensity mask to punch out all pixels everywhere in the data set above some threshold intensity. So that's running right now. It's finding all the high intensity pixels, says it's done, and then it gives me the mask. Okay. And then once you're done designing your mask, you can add your mask to your workflow by saying .add mask. And then I'll run that. And now it's been added. And so now to actually apply the mask to the data and to actually punch out those Bragg peaks, I can use the punch function, and then the resulting data is stored in the punched data set, which lives within this object here. So that works just like the data we saw earlier. We can index it just like a regular data set. And so I'm going to plot it with these specific parameters so you can see the diffuse scattering a little bit better. And you see we punched out the diffuse scattering very nicely, or we punched out the Bragg scattering very nicely. Okay. All right. So back to the PowerPoint. The next step would be to fill in those gaps. Okay. So we have to do that, we have to apply you can think of it as like a Gaussian blur, if you're familiar with it, like applying a Gaussian blur to an image. But really mathematically, this is a convolution of a three-dimensional like Gaussian blob with your data set. And so what this is doing is it's basically taking the values around the pixels that aren't there and summing those values multiplied by this Gaussian function. So the Gaussian function, you can change the size of it. So here's a Gaussian with a standard deviation of 1. It's really tiny. Here's one with a standard deviation of 5. It's a little bit more spread out. Okay. And depending on how big your Gaussian kernel is, the more smoothing is going to happen. Okay. So you don't want to overdo it. You don't want to like really blur out your data so that you lose all the information. But you want to have a blurry enough Gaussian that it's able to fill in the gaps completely. So you want to make sure there's no holes left in your data. Okay. So for that, we're going to use this function called setKernel, and we're going to call this Gaussian 3D kernel function. And that's already typed out for you, but you can change the standard deviation and you can change the size and like pixel dimensions of the Gaussian that you're using. The main benefit here is that because the Gaussian is only 10 pixels wide, it's faster. But the more spread out your Gaussian is, the bigger of a pixel array you're going to need to like capture the whole Gaussian shape. So there's a balance you have to strike between the size and standard deviation.
Hey, Stephen, two
Yep.
questions. So how do you know like you haven't overdone it when you try to like do the select how much standard deviation your Gaussian has?
Mhm.
Yeah,
So
and
yeah, go ahead.
I go ahead and answer that first question.
Yeah, I think you want to do enough to ensure there's no remaining gaps. So that's what this looks like, right? There's always artifacts at the edges, so you can ignore those. But um, you want to do it enough that you fill in the gaps, and also blurring it out can help smooth out the detector artifacts that you don't want, like in the chest data particular, there's like a lot of like ripples and things like that in the background, which you can effectively get rid of. But like once I have a clean data set, this is just with a standard deviation of 1. If I apply a standard deviation of 5, I'm really like losing a lot of the definition of the diffuse scattering. So it's like you decide when it's good enough, but there's no reason to make it this blurry.
I see. And when you try to like work with your mask, let's say you have a data set that has for some reason more intensity in like the lower right section of your HK plane. And yeah, it seems to be a bit more asymmetrical. Like how do you select a good standard deviation then?
Um, for the Gaussian, you mean? Is that what you're saying?
Yes.
Um, Maybe I don't understand the problem. So you're saying like this part, let's say this part of the data set's really bright for some reason, right? Just the bottom left corner is really bright.
Sure, yes.
It would stay bright after the convolution with this Gaussian.
You don't have to worry too much about like how much your standard deviation you choose, right? Because
Mhm.
still it's gonna have this bit of a gradient that you have to work with, right?
Yes, but like if I compare the size of this Gaussian to like the actual data set, it's like this big. It's tiny, right? So the data over here will stay the data over here. It's not like this data is going to affect the processing of the rest of the data. Also, you
Yeah.
got to think about like if that corner of the data set is artificially bright versus like structurally bright. So if it's artificially bright, you may want to like symmetrize using a different part of the data set, right? Yeah. Okay. So this is skipping ahead a little bit, right? But after we convolve, we get these images here. So let's go ahead and try to get that. I think, there's one point that I wanted to get at here, which is, if you're familiar, right, the peak width of anything in reciprocal space corresponds to a correlation length in real space. So the more you blur your reciprocal space data, the less correlation length you're going to have in real space after you do the PDF. So there's a trade-off between these two. Okay. So let's go back to this guy here. So step 3 here, right? We're going to fill in the missing data. Here's where we set up our kernel. Okay, so I'm going to choose a standard deviation of 1, and you can play around with it as you see fit. And I'm going to go ahead and plot the kernel so you can see what it looks like. Zoom out a little bit. And then to perform the actual interpolation of the data, I use this interpolate function. It's going to go ahead and run, and it should be quick. Should be quick. Okay, took 0.26 minutes. And then we can look at this interpolated data set that then gets created, and we see that it's nicely smoothed out. Okay, so that's what it looks like with a standard deviation of 1. And if I went back and say did a standard deviation of 100, I'd probably have to make my bin a little bit larger. Let's see what it looks like. Okay, so yeah, see, clearly I overdid it. All right, there's no structure. All right, let's go back to what we did before. So a standard deviation of 1 was good enough. All right. Okay, so the next step is to taper the edges of the data. And so for that, I'm gonna again jump back to the slides here. So if you're familiar with Fourier transforms, or if you've taken GymSpec's 209A class, you know that the any hard edges in your diffraction data set are gonna be represented by this what is called a top hat function. Okay, this top hat function is sort of just like this rectangle. And if you take the Fourier transform of that rectangle, you will get this wiggly guy called the sinc function. Okay, or in 3 dimensions, I guess it's the Bessel function. So in order to avoid ripples, like artifacts in our data set after the Fourier transform, we need to smooth out the edges of our data because effectively our data is just a rectangular box, right? Because there's a hard cutoff to the edge of the detector. So what we'll do is that we'll then take the edges of the data set and we'll taper them off to 0 in a very smooth manner. So right now what we have, right, is we just have this edge, this hard edge of the data set right here and right here, right? And so if I take the Fourier transform, it looks pretty crappy, right? I got a lot of like really weird oscillations in my PDF and I can't really tell what's going on, right? Now contrast that with if I apply a tapering function to taper off the edges to 0, doesn't the PDF look a lot better, right? I can see that there's like these size effect correlations, maybe what looks like a displacement correlation here at these integer positions. And so already I'm getting good information out of my data set that I wouldn't have been able to get had I not tapered it. All right. So as with most of these steps, there's a compromise to be made, right? You need to smooth it out as much as possible. You need to minimize the cutoff effect, but you need to maximize the range of reciprocal space that you can use because you're, of course, losing information when you do this. So you can change the slope or change like the aggressiveness of how you taper it. And this is maybe, not that helpful advice if you already have your data, but when you're planning like a scattering experiment, you want to go in with a really high incident energy on your beam because your high incident energy will allow you to get a wider range of reciprocal space, as designed. So your data set will artificially cover, or like from the get-go, cover more of reciprocal space. So this will impart less information loss to your data. In this experiment, we went up to like, I think it was 26 keV incident energy. So 26 keV for this compound got us up to like H equals 5 and L equals 8. So that's what we got. Okay, well, okay, let me backtrack. This is not an experiment. This is data that I created by hand. So in the experiments that we have in our lab, most of the data sets are 26 keV, which gets you about 5 to -5 in reciprocal space. Okay, so let's go ahead and what that looks like in the code. All right, so we're gonna check out the window that we're gonna apply. So the window that we're applying to the data is called a Tukey window, okay? Named after, this person with last name Tukey. So if I set the window to be a Tukey window, I have to use this function, and then I get the window stored in this window variable. Okay, so if I plot that, it looks something like this. I can also tune the breadth of that window by changing these alpha parameters. And these are along H, K, and L. So if I plot it with alpha equals 0.5, you can see that the tapering is a little less aggressive, right? It tapers off a little further out in reciprocal space. And I can lower it down to something like 0.1. Then you'll see it's really not aggressive, okay? But if I tapered it this much, I would still get a lot of ripples, right? So we'll play around with that in a little bit. So to apply the window to our data, we're going to use the apply window function. So I'm going to go ahead and use the most aggressive window I have, which is 1.0, 1.0, 1.0. And then the data gets stored in this tapered data set. And that's what it looks like. That's kind of what we saw in the slides, right? Okay, now moving on. Feel free to interrupt questions. So the next step, or the next consideration, I guess, like we already have a good data set, right? If I Fourier transform this data set, I get this thing on the right. I'm skipping ahead a little bit, but like this would be good enough, right, for interpretation. However, it's a little pixelated for my taste, right? So usually when people publish on DeltaPDF, if they have like a really nice data set, they increase the resolution arbitrarily. So we can actually do that by effectively recognizing that effectively the range in reciprocal space corresponds to the bin size after the Fourier transform. Okay. So, I mean, one way of thinking about this is like if you think about like electronic structure, right? Like when you think about the discrete energy states in like an EK diagram, right? Every spacing of the energy states in K in reciprocal space is determined by 1 over the lattice parameter or 2 pi over the lattice parameter. This is the same principle that like the range of your reciprocal space gives you the discrete steps in real space. So the wider we can see in reciprocal space, the clearer we can see in real space. And unfortunately, we don't have any more data, but we can pretend we do by just padding our data set with a bunch of 0 values. So that's what that looks like. Okay, so we're just taking our data set and we're just taking the array and just adding a bunch of 0 bins all the way around in every single direction. And what that looks like in real space is then now we see the features a lot more clearly, right? You can see that between the previous slide and here, big difference. Okay. So this is a way of artificially improving the resolution of the data, but it can drastically increase the computation time for large data sets. Because your data sets are like our data sets are usually like 2000 by 2000 by 2000 pixels. So one strategy then to reduce the file size or reduce the intense like computation use on your computer is to artificially like rebin your data from the start to make it like lower resolution, your scattering data make your scattering data lower resolution. And that way, you're effectively reducing the strain on your computer at this stage. Okay. So let's go ahead and see what that looks like in terms of the code. So I guess we're here. So padding the data with zeros, you can use this pad function and pad the data. So I'm just going to pad the data in the H and K plane. And I'm not going to pad it along the L direction because I just want to look at a 2D slice. I don't care about the resolution out of the plane right now. And it's going to save us some time. So I hit pad, and then I can plot the padded data. And you see it looks something like this. Okay, so there's a lot of 0 values around our data. And then I can perform the Fourier transform by using this function. So let me go ahead and run that. And then it'll just take some time. That's too slow. Hold on. Let me not pad the data as much. Start 100. So right now it added 100 pixels on the right side, 100 pixels on the left side, 100 pixels on the front and back, and then the top and bottom. Well, yeah, not the top and bottom, because I only had one. Man, okay, it's taking some time. Let me not pad it anything at all. It's a good time for questions.
When you're doing the Gaussian blur across like the and filling stuff, are
Mhm.
you doing that across like all three axes, or is it just like in plane?
You can choose.
Oh, really?
Like,
Nice.
for example, if I wanted to just do the convolution in plane, I would
Mhm.
simply make this array a 2D array. So instead of having a 10 by 10 by 10 Gaussian, just have a 10 by 10 by 1 Gaussian. And then it would effectively be like a pancake. Okay. That's helpful if you're doing, say, like I don't know, maybe just a lot of artifacts that are like out of the plane, or maybe there's a lot of structure in reciprocal space that's out of the plane, and you don't want that to like smear into the neighboring planes. So yeah, you might strategize and say, let me use the data within the plane to basically heal the holes, but out of the plane, I don't want any other plane interfering with any other plane. Okay, good question. All right, so yeah, we see we get our Fourier transform. I could change the limits here a little bit. I could divide the data set by some number, make it easier to see. Yeah, so okay, we see that there's like some like strong features at these coordinates, okay? So we know the answer already, right? We know that there are vacancies, and we know that there are atoms that are moving around those vacancies, right? So like we're kind of cheating. We have an idea of what the answer is already. So let's go ahead and talk about how we interpret the 3D delta PDF. It's not as intuitive as you might think. So what I have over here on the left is a real space model for a vacancy and the atoms around it that are displacing. And then the atoms one coordination shell out shouldn't be affected at all, right? These atoms over here are all totally unmoved. Okay. So let's first examine what this little dipole at integer positions means. So this is the nearest neighbor. It's a nearest neighbor correlation. In order to interpret our data set, we're going to have to look not just at the vacancy and not just at the vacancy's nearest neighbors, we're going to have to look at everybody's nearest neighbors. So anytime there's an atom and another atom that are one direction away, one unit cell away in the x direction, we have to consider that. Because as we saw earlier, right, all interatomic correlations are going to get superimposed on the same PDF. Okay. So visually, let's see what that looks like. So one of the pairs of atoms that is a nearest neighbor is that guy, right? So what changed as a result of this vacancy in the local structure? So what I'm plotting here is that I have the previous, like the initial vector, and then the final vector. So this is before and after the distortion. And what do we see? Okay, we see an expansion of that interatomic distance. Do we agree? Okay. So that is going to contribute on this vector, it's going to contribute something that looks like this, right? There's going to be a decrease followed by an increase. So effectively, the peak is moving to the right in the PDF. Yeah? Okay. So that's not the only thing that's contributing here, even though it looks the same. There's also this guy over here. So what's happening with this pair? This vector was the initial vector, and now that one has also expanded. So we're going to get a superposition of these two features in the delta PDF. Okay. So that still looks the same, right? But what other changes can we find at nearest neighbor distances? So one of the vectors is actually this guy. So this atom and this atom had a change in their relationship, where the final vector has actually been moved up. Okay, so what that creates is an upward shift at this coordinate in the PDF space. Okay, so it's these two plus this upward shift that's all being added at this position. But to cancel it out, there's another one. That's where the change in the interatomic distance has moved down. Okay, so that imparts a downward shift that then cancels out. So effectively, what we're left with is this expansion. Okay. Questions? I had to squint at this for like an hour. So cool. All right, so it's about to get more complicated. So ask questions now.
Question.
Yeah.
So I'm trying to think about like what exactly you're looking at in the space that you have plotted there. You have a real space positions of a single atom, or you have like the whole unit cell there.
Well, one unit cell is, well, all these tick marks right here are unit cells, right? So like x equals 1 is 1 unit cell away.
I see. So you're looking at a certain specific atom position with respect to a unit cell, or like within a unit cell?
You're looking at every correlation that exists 1 unit cell to the right of any given atom.
Okay. How
Okay,
do you
so like, go ahead.
atom you're looking at that?
Sorry, say that one more time.
How do you know what atom you're looking at?
That's a good question. We know, for one, that this delta PDF, we're only looking at the changes in the local structure. So when I'm looking at the real space model on the left, I'm only pointing out the atoms that have changed, right? Or the atoms which contribute to pairs that have changed, right? So that's one way of answering your question is right now I'm only thinking about the atoms whose local structure is different than the average structure. So that's why I'm looking at the at pairs where the one of the atoms has moved, at least one of the atoms. Okay. Then I also have to think about what I'm seeing in the PDF is every single one of those sets of pairs superimposed on the same coordinate. Because we lose all information about what atom was like at the origin when we do the PDF. Okay. So we're not just seeing one atom or one pair of atoms, we're seeing every possible pair of atoms that exists where they're 1 unit cell apart. Okay, so you can imagine that for a real crystal, this would get very complicated very quickly because, in this picture, we have one atom and another atom, and they're the same atom, and they're a unit cell away. I guess that's always true for real materials. But there's only one site, right? But you could have equivalently a second site with a different atom, and then it also has a neighbor that's a 1 unit cell away, and it might have different motion or different correlations. So a lot of things are going to overlap here, and it's hard to interpret, as we'll see in a second. So don't worry about fully understanding the like every possible type of correlation, but we do want to get a basic idea of like what we're looking at in terms of these like dipole looking things. Okay. Any other questions before I move on? All right. So we looked at 1 unit cell away to the right, right? Let's now look at 2 unit cells away to the right. So what's going on here? So one of the most obvious correlations, which is 2 unit cells apart, is this one, where you have two atoms that were 2 unit cells away and they contract towards each other, right? Okay. So that contraction is going to be manifested as this dipole, okay? Where now the red intensity, the increase, is now closer to the origin, right? It's to the left. So that represents electron density sort of shifting leftward towards the origin. Okay, so that interatomic distance is shortening. And then we also have this pair where that interatomic distance is increasing, right? And the interesting thing is that even though those two seem like opposites, they're not equal in magnitude. And because we can resolve the positions in the delta PDF space, we also actually realize that these two dipoles are not actually perfectly overlapped, okay? So these two aren't going to cancel out because their intensities are different, or their magnitudes are different, and because they're not at the same exact position. And so what we get with the overlapping of these two is something that looks like this dumbbell shape. There are other correlations that exist at 2 unit cells away, but as we saw in the last slide, those two will cancel out. Okay, so I'm just going to gloss over those. But when we have the overlapping of these two dipoles, we get this displacement-like correlation, which looks like sort of two dipoles connected at their ends. Okay, I'll let y'all stare at that for a little bit. Cool. Shall I move on? Okay. All right, so now this nightmarish looking thing that exists diagonally, right? It's like quadrupole four-leaf clover looking business. This one's a little bit more of a nightmare to interpret. Uh, so again, we're going to look at correlations that are 1 unit cell to the right and 1 unit cell up. So the first one I can think of is that one, where there's a change such that both of these vectors, before and after the distortion, they've picked up some translation to the right. Okay, so they're both going to constructively interfere with each other. And they're both going to constructively interfere with each other. So I'm going to plot those in the same term in this sum down here. Okay. I know this one looks like it's shifting to the left, but you got to connect vectors at their tails, right? So this new vector is actually pointing a little bit more to the right. I was confused about that for about 30 minutes yesterday, so think about that. The other correlation is these pairs right here, and those are both moving upward. Again, this one is moving up, and this one, the new vector is also picked up an upward component. So those two are going to constructively interfere. And then the last one is these contractions, right? These two atoms, as they collapse towards the vacancy, if you think about standing on one atom, it effectively feels the other atom moving closer to it along the diagonal direction, even though one is moving to the right and one is moving downward. From each other's perspective, they just see each other getting close. Okay, so that's going to impart some contraction along that direction. So if I add up all these, I get that four-leaf clover looking thing. Okay. It's very tempting to just eyeball the PDF, right? And just say, all right, I know exactly what's happening here. Atoms are moving away from the vacancy, right? Because this is a positive shift. It seems like atoms in a diagonal direction tend to move in this diagonal direction because there's increased intensity here. There's some displacement correlation over here. Like you can stare at this and try to come up with some story, but unless you have a model in your head of what's going on, you can easily mislead yourself into telling yourself the wrong story. Okay. So the reason I walked you through that is to sort of build an understanding of what these things could mean, but in general, direct interpretation of the DeltaPDF is really challenging. Okay. And we've looked at one of the most simple examples already. We don't always have a good understanding of the underlying correlations when we do our diffraction experiment either. More often, we're using the diffraction data to try to figure out what those correlations are in the first place. So we were lucky in this example that we knew what was going to happen from the get-go. So that made the interpretation a little bit easier. And also, when you're trying to publish this data, it's really challenging to argue what your interpretation is, even if your model is, somewhat physically reasonable. Okay. So instead of just sort of claiming that you are right, it's useful to turn to computational modeling and build a disordered crystal on your computer and then calculate what the scattering should be. That way you can really get your experiment to line up with your interpretation. Okay. So the software that we use for simulating diffuse, one of the softwares that you can use for simulating disordered crystals and diffuse scattering is this software called Discus. Okay, Discus is diffuse scattering und in German structure simulation. It runs only on Linux, but you can install it on Windows. You could probably install it on Mac too. You definitely can install it on Mac. I don't know why I didn't list that here. But anyway, you can install it on Windows by installing this thing called WSL, the Windows subsystem for Linux, which is what I have installed on my computer. But that's kind of a pain in the butt to install. So like, yeah, if you're interested in installing it, like I'm happy to help. It's just a little bit annoying to get that up and running. It's very easy to get it up and running if you have a Linux system or if you have a Mac, I think. So this software, it allows you to write code that basically builds a virtual sample with chosen defects, chosen disorder, and you can add in correlations and then simulate the resulting diffuse X-ray and neutron scattering that results from that. And also, additionally, you can take experimental data and then refine a structure directly from the data, which is also very useful. And what that allows us to do is it allows us not only to simulate the diffuse scattering, but it also allows us to pick up a simulation of the DeltaPDF, because we can apply the same transformations that we just walked through to the simulated data. Okay. So in order to create what we call a forward model, and by forward I mean we're starting from an atomistic picture and then going forward to the scattering data. We can start with adding in some disorder, creating correlations, simulating the scattering, calculating the DeltaPDF as we just did, and then comparing the scattering and the DeltaPDF to the experiment to strengthen our interpretation. So, I don't expect you to remember all of this, but this is more of just a resource for you. What you need to feed into these types of simulations are structural information, right? You need to have some picture of your unit cell. So you either need a CIF file, or you can use a cell file, which is, it looks like this. It's basically just a dumbed down CIF file that Discus can read. Discus can also totally read CIF files. Or you can feed in a structure file. And the structure file, it doesn't have to be the unit cell. It can be an entire like supercell with disorder built in. So you need that structural information in some file. So here I have like a simple cubic unit cell where I just have copper at the origin, and then I have 5 angstroms and then 90, 90, 90. And in addition to that, you need a script that is able to generate the disorder and, if you want, generate those correlations. So these are macro files. So these are the scripts that you would run, and they use a mixture of Discus unique syntax and Fortran syntax. Pardon me. So the simulation I'm going to show you today is basically going to recreate the data that we just looked at. So you could pretend that the data we just solved was an experiment, and now we're just going to recreate a computational version of that. In reality, what I gave you all for the example was already the output of the simulation, so it's going to look identical. So these scripts, what it's going to do is it's going to load the structural information, generate a big old supercell. It's going to randomly create vacancies within that simple cubic structure, and then it's going to relax the nearby atoms to get them to collapse inward towards that vacancy. And then it's going to call some other scripts that do the plotting and the Fourier transform. Okay. And just to highlight, out of this, you can export disordered CIF files, which you can then feed into Vesta for plotting. And then you can also export Nexus files that you can then analyze the same way we did the experimental Nexus files. Okay. So to walk you through visually what that's doing, so first it loads the unit cell. So as we saw earlier, this was just a simple cubic unit cell. So that's going to be represented by this little blue dot here, right? Little square. And then it's going to generate a supercell. So what I generated here is a 20 by 20 by 20 by 20 3-dimensional supercell where all of these atoms are just copper. Then I can have Discus randomly create vacancies. So I told it basically I want 3% of the atoms to be replaced by vacancies. Okay, so that's what those little black dots are. And then I told Discus, find all the atoms around those vacancies and then move them towards the vacancy. So that's what that looks like. So I make a little GIF so you can see the change. So I'll just show that off for a second. All right. So that's one way to build, you can just build a forward model like that and then simulate the scattering and then, do all the analysis like we just did. The other thing you could do is what's called Monte Carlo modeling. Okay, so this is where you can generate very complex short-range correlations. And so the theme for Monte Carlo modeling is, you have a supercell, you add in some disorder, but then you define some energy terms, right? You have some interactions between the sites that then over several iterations of your Monte Carlo simulation, you find the ground state of whatever Hamiltonian you plug in. So one example would be, the nearest neighbor icing model, okay, where basically we're adding up interactions between neighboring sites, next neighbor sites, I and J, and we have some icing degree of freedom, which could be an icing spin for those of you who are familiar with magnetism, or it can simply be a binary degree of freedom, something that could be a 0 or a 1, analogous to a spin up or spin down. And then we impart some energy penalty or energy gain for having the same state on both sites. So if this J coefficient is positive, then nearby sites will want to have the same state. And if they are opposite state, there will be an energy penalty. And then if J is negative, we'll get nearby states that have the same state to be disfavored. And then we'll be able to energetically favor an alternating pattern. So you could build quite complex short range order from this. So what Monte Carlo modeling does then is it has this loop where it performs a move, which the move can be defined in a variety of ways. It can be either swapping elements between two sites, it can swap the displacements of two sites, or it can shift the position of atoms. So this is an example of swapping where this atom and this atom were chosen for the move and then they were swapped. This is an example of shifting where one atom is chosen to be randomly displaced along a given direction. And then this is an example of swapping displacements where every atom has a displacement to start with, but then you basically trade displacements between different sites. Okay, and you can build a lot of useful things from these simple building blocks. So after the move is completed, your simulation will calculate the energy of the new structure after the move. And if your energy decreased, that means you're moving towards the ground state, right? So you're going to accept that move as a step in the right direction, and then you're going to try again. If the move ended up increasing your energy, you reject it most of the time, but you accept it sometimes so that you don't get stuck in like a local minimum state. You want to find the true ground state. So it is helpful to occasionally accept a bad move just to spice things up. So if I run the Monte Carlo simulation in Discus, which I'll show you how I do in a second, these are the results. So if I plug in J is half, and these are in units of kBt, so that's why there's no coefficient. So this should really be J over kBt. If J over kBt is 0.5, I get very strongly ferro-like or ferromagnetic-like occupations of this two-atom alloy that we saw earlier. If I have a weaker interaction strength that's still positive, my short-range order becomes even more short-range, right, after finding the ground state. And then if I have weak anti-ferromagnetic or anti-ferro-occupational correlations, I get a local, very, very short-range checkerboard pattern. And if I turn up that strength to be more negative, I get, more extended domains of that alternating pattern. Cool. That's the end of the slides. I guess I'll just flash this up here. There's a lot of useful reading websites. There's a wiki. All of these things talk about different, things that are related to what we talked about today. So there's this book that goes into the theory of diffuse X-ray scattering, which is a really good discussion. This paper is particularly broad, so it doesn't just talk about like the things that our group works on in the Wilson group. It talks about like molecules and metal organic frameworks and supermolecular assemblies and how short range order can be resolved in those types of systems. And then the rest of these are just for coding everything up. So just to give you a quick preview of what Discus looks like and how powerful it can be. If I can find my window. All right, can you all see this? Yeah? All right, so I have some scripts here. These are all various scripts that I have. Let me just make sure I'm opening the right one. Oh, 3D. So I have a script here called vacancies, and that's going to generate the data we saw earlier. So I won't bore you with all of this. You can read through this on your own. But I guess the main things are the main things we can tune are the amount of vacancies. So when I created that data set, I said, replace 3% of the atoms with a vacancy. And then I changed the displacement in percent of the lattice parameter. So right now, when there's a vacancy, the atoms nearby will displace in an amount of 15%. And if I wanted it to be larger, I could change this to say like 25, and we could see how that affects the scattering pattern. So I can run, let's see here. Let's go to the vacancies folder. And let's run the vacancies script. I have to open Discus first. So this is the Windows subsystem for Linux. And then if I run Discus, I get this nice little window, and then I can just run the vacancy script that I just wrote out. And you see it runs through a bunch of stuff. Basically runs all the code that's in that document. And you see now it's calculating the Fourier transform, which is to say it's calculating the scattering, not the PDF. Okay, that takes some time. I swear it was faster than this when I ran this example before the workshop. There we go. Okay, it's done. Okay, so now it created this vacancies underscore calculated.nexus. And then if I go back into our folder here, I see that just popped up here, right, seconds ago. And let's say I use this same Jupyter notebook. Let me just duplicate it. So let's do vacancies where this was 25% change of the lattice parameter rather than 15%. So let's, instead of the experimental data, let's load the calculated data. And if I run everything, you should be able to see that the scattering pattern will look similar, but not exactly the same. Oh, the Nexus files need to be loaded differently. Yeah, the Discus format Nexus is slightly different, so I have to use a slightly different function. So that'll be load Discus Nexus file, and then I should be able to run everything after that. So let's run selected cell and all below. Okay, so you see the diffuse scattering looks slightly different. So if I compare side to side, yes, I can. So you see that we still have this um, size effect like sort of diffuse scattering that's closer to the origin, right? It's asymmetric about each Bragg position, but the texture is very different, right? So the structure of the diffuse scattering uh, really encodes a lot of information. And so just with a change in the displacement, you see that the pattern looks like, wildly different around these sort of like clusters of diffuse pockets. And then it's probably done with the PDF by now. Ah, what happened? Oh, it's because I changed this to 10. Okay, let's just see what changes take place in the PDF. Come on now, it's the error. Hmm. Let's look at the PDF on changes. That was our original PDF. There's our data. There's our diffuse isolated data. I use that 2Q window. There's our tapered data. Didn't pad the data this time. Okay, so you see it more or less looks the same, but there are shifts in the positions of these things, and there are shifts in how sort of extended they are in real space. And so the bigger the displacement, the sort of more spread out the features in the Delta PDF will be. All right, that's really all I brought today. So thank you all for coming. I'm happy to chat about whatever. If you have any questions or use cases. I'll stop the recording now, I think.